Alright, so far we talked about a typical utility function, then a production function, and the last one I want to introduce is a typical cost function. And a typical cost function is inversely S-shaped. But let's just review again. So first we had utility, and we drew a utility function, something like, so we were consuming a good X, and then the total utility was going up, but at lower and lower rates. And we call that the law of diminishing, that's supposed to be law of diminishing marginal utility. Okay, and then we looked into production. I'll do that here. So that reads law of diminishing marginal utility. Okay, so then we talked about production. Okay, production. And we said we have an input, like labor, and we convert it into output, like X. And then we said the production function is typically S-shaped. So it looks like this. Initially output grows faster than input, and then we get something like this. And then we derived the marginal product. The marginal output. And we said, well, that looks like something that's inversely U-shaped. And so the idea was that initially when we have more workers, the output marginally keeps on going up and up and up. And maybe here there's a maximum that corresponds to the maximum marginal output. But then the slope becomes again flatter and flatter. Okay, this is what we already covered. So the next thing is we need to look at the total cost function. So a total cost function. So when it comes to total cost, what we do is we want to know how much does it cost to produce X. So we take the output and convert that into total cost. And then typically people are also interested in things like marginal cost, average total cost, and average variable cost. Okay, so how does a total cost function look like? Well, as it's already said here, it's inversely S-shaped. But there is a component here in this example 5 that is independent of the X. That is actually fixed cost. So there's definitely a fixed cost share. Fixed cost, that's supposed to be. And then an inversely related cost function looks like this. So that means that the output, as the output increases, the cost increase, yes, but at the diminishing return. It's a little bit similar to the utility function. So what's the explanation for that? The explanation is that if you produce more and more output, you need more and more workers. But the workers initially, they can specialize. So think again about your kitchen. So one specializes in doing this, the other one doing something else, and output increases. But in the real world, you have to pay every worker the same wage rate. That means the more workers you hire, the more they specialize, the more output they produce. So, but the cost stays the same. Each worker costs you the same. So that means as you produce more output and hire more worker, the total cost, yeah, they increase, but they increase at a diminishing rate simply because those workers that you hire, they become more and more productive. But again, there is then some kind of an inflection point. So initially here, you produce something and total costs go up. Then you produce more, you hire more people, but they become so, they specialize, and they become maybe in their sum more productive, but they cost the same, but they produce more and more, their marginal output goes up. So that means that the total cost increase, but they increase at a diminishing rate. And then there's maybe some point of inflection. And then, if the workers already start blocking each other or standing on each other's feet, that means if you want to produce more and more output, well, the cost keep on going up. So that means a marginal cost function typically looks like this, like U-shaped. And then we also still can look at average total cost and average variable cost. And the total cost, average total cost, is simply divided. If you divide the total cost, okay, so let's say average total cost, ATC, is total cost divided by X. Okay, so in this case, we have 0.05 x cubed divided by x, so that cancels out. Plus minus 0.75 x. Okay, now I start a new line, plus 4 plus 5x. Okay, and the average variable cost, so the variable part is only this. This is the total variable cost, and this is a fixed one. It's a fixed term, it's a fixed cost. So then the average variable cost is simply 0.05 x squared minus 0.75 x plus 4. That's it. Okay, and it actually turns out that average total cost look like this, and average variable cost like this. But we'll stop the theory here and we'll just draw this equation. So let's take this function and draw it for the domain from 0 to 10. Okay. Okay, so this is the function. Oh, okay, then I see what happened before. Okay, just need to clean up here. Okay, so let's start here then. Here's our Okay, so here's our function. And I'll just do it here, so we can't really see it, so let's just be in the yellow cell. There is our function, but it seems like I need to change. I don't know why it can't be seen, but we can see it here. So this is our total cost function, so let's create an x, and let's just do that here. X, and I do it from 0 again to 10. So I create a column that goes from 0 to 10, and this time I do a step value of 0.1. So I highlight everything, then we go to Home, Edit, Fill, Series, step value 0.1, stop at 10. Okay, so now we have a column from 0 to 10. Okay, so now the total cost function, which we have here, so 0.05 times x cubed, so equals 0.05 times x cubed plus, what was the second? The second term was minus 0.75, okay, minus 0.75 times x squared plus 4x plus 5 plus 4 times x times plus 5 plus 5. Okay, so now we have a total cost function, and this should be equal, but this should give us a inversely S-shaped function. Okay, so now I can delete that, and let's put it on the right spot. Okay, so this is our total cost function. Let's highlight everything and let's see how it looks. Recommend the chart. And you see, in fact, it is inversely S-shaped. Okay, let's put that here. Okay, so next, let's also do the marginal cost and draw that as well. And let's do the marginal cost function here. So this is the total cost function. What I do is I just quickly delete all that ink, and let's derive the marginal cost function. Okay, so with the 3 goes in front. 3 times 0.05, that's 0.15 x squared. We have to subtract the 1 from the 3. Minus, the 2 goes in front. 2 times 0.75 minus 0.5 x plus 4. Okay, so that's the marginal cost function. So let's put that in here. So I said this is equal to 0.15 times x squared, then was it plus 1.5 times x plus, was it 4? Okay. Okay, this is 3 times, that is 0.15. Okay. Got here. Okay, the 3 goes in front. 3 times 0.05, that's 0.15 times x squared. Then plus 0.5 x, that's correct. And then, yeah, plus 4. Okay, good. So now we can copy that down. And I think there's something wrong. 0.5, so this is 0.15 a2 squared plus, oh, there was a minus, I believe. Oh yeah, that's a minus here. Okay, that looks U-shaped because the values go down and then they go up again. Okay, so that looks correct. Then we can calculate the average total cost. That is simply equal to the total cost divided by x. And of course I can divide by 0, so that's a pretty high value, so let's just blank that out. And then average variable cost, so that is the same. I'll just take the total cost, but then I have to subtract that fixed term, so I actually can just take this term without the plus 5. Okay, and then I just divide everything without the fixed term. So you take this one, okay, and then let's enter that here. Oops, that was wrong here, needs to go. Equals, and I'll put parentheses around. And then we divide by x. And again, I get a error message, but I can blank that out in a second. Okay. Okay, so now let's draw this. On the x-axis we put x, then average total, average variable. So I highlighted everything that I need to draw the graph. Insert recommended charts, and we take this one here. Oh, I forgot marginal cost. Insert recommended charts. Okay, let's take this one here. So that doesn't really fully look like yet. Okay. Okay, so what I do is there are like those very high values. This graph doesn't look like what I drew here. We said earlier that marginal cost should look something like this. Average total cost should look something like this. And average variable cost should look something like this. So the problem is that we have those very high value from the average total cost function. So I just blank out a few. Maybe if I blank those out, you can already see it looks much more. I can blank out some here as well. Okay, So now we have here the blue one, the marginal cost, average total cost, average variable cost. Anyhow, so the point of this exercise was really to expose you a little bit to typical cost function. We have talked about the utility function, then about a typical production function, and then we converted it into a cost function. And we also drew them in Excel, which is a useful exercise. And in the next one, we build on those and we do a little utility maximization problem. And then I hope everything will come together. But let's do that in the next video.